So this is part 2 of how to solve acidic and basic salt problems. And we're going to be using problems 9 and 10 from your guided practice worksheet. And you may want to have these 3 steps kind of handy as we practice these, just to refer to, because these are the steps we're going to follow to calculate the pH of these solutions. Okay, so let me get everything lined up here. So problem number 9, let's just take a look at this. It says calculate the pH of a 0.3 molar sodium fluoride solution. So if you look at this particular salt, you can tell that it came from sodium hydroxide and hydrofluoric acid. Well, this is a strong base and this is a weak acid. So that means this is a basic salt. So this should be a pH greater than 7 when we're done. Now it gives me the Ka for HF. And remember, in the steps, one of the steps said you need to make sure you find the Kb if it's a basic salt. If it's a basic salt, you need Kb for F minus. So what they've done is they've given you the Ka for HF because we need the Kb for F minus in a few minutes. But let's go back to the first step. The first step was to dissociate your salt 100%. This is a soluble salt, so sodium fluoride dissociates 100% into the sodium ion and the fluoride ion. Now remember, if it's 100% dissociation, and I'm only going to ice this one time just to kind of remind y'all of, and in this case, since this is 100%, the E stands for end, not equilibrium. So we have 0.30 molar, initially 0 and 0, minus 0.30 plus 0.30 plus 0.30. So that means at the end of this dissociation, we have 0.30 molar of the sodium ion and 0.30 molar of the fluoride ion. Now this is important because this happens to be the conjugate base of the weak acid HF. Now in your steps, back in your notes, if you refer back, it said if the salt was basic, it said take the anion of the salt. This is the anion because this is a basic salt. And this is where you're going to do your equilibrium problem. So this is the equilibrium problem. This was the stoichiometry problem. Okay? So you're going to take the anion, F minus, and what does it say to react it with? That's right, it says reacted with water. Now remember, water is a liquid. It is necessary for the dissociation, but it will not show up in your law of mass action. So now this is going to be the equilibrium problem. Notice how I used equilibrium here. Now think this through. If F minus is a conjugate base, he is a proton acceptor. So he's going to pull a proton off of the water, and that's going to form HF. And what it leaves behind off of the water is the hydroxide ion. Now remember, this is an equilibrium problem at this point, so we're going to define our shift in terms of X. Now the reason we need Kb for F minus is because this is the reaction where we need the Kb for the conjugate base F minus. So to find Kb, we know that Ka times Kb always equals Kw. So we need Kb. That means Kb is going to equal to Kw divided by Ka. Now remember, Kw is 1 times 10 to the negative 14. That's the ion product constant. And you divide by the Ka of HF, which is 7.2 times 10 to the negative 4. So that's going to give us a Kb value. Go ahead and plug that in and see what you get. 1.4 times 10 to the negative 11. So we're going to use this in just a few minutes. You always kind of got to go to the side and calculate that. Basically, if they give you Ka, you need Kb if it's a salt problem. If they give you Kb, you're going to need Ka. So you're going to have to do this formula. All right, so now pull this concentration in. 0.30 is the concentration of the fluoride ion. Now remember, water's a liquid, so we just kind of put dashes there, and we'll put 0 here and 0 here. Now we're going to define our shift in terms of x. So minus x, plus x, and plus x. Remember, you can neglect x here, so since we have an initial amount, and this is weak, so 0.30, x, and x. All right, so let's set up our law of mass action. So Kb is equal to concentration of HF times the concentration of OH minus divided by F minus. Don't include the water. So we're going to pull the Kb value from here. 1.4 times 10 to the negative 11 equals x squared over 0.30. So cross multiply and then take the square root, and that's going to give you for your x 2.0 times 10 to the negative 6 molar. And what we have found, and this is where you got to look back up here, we found hydroxide. So x in this case represents the hydroxide ion concentration. So if we take the negative log of this, we will have found the POH. So the POH is equal to 5.69, and the pH equals 14 minus 5.69, which is 8.31. Now, again, since this was a basic salt, we should have anticipated a pH greater than 7, and this makes sense. So we are finished with this example. Let's look at problem number 10. Similar kind of problem, except here the salt comes from a weak base, NH3, and a strong acid, HCl. That means this is an acidic salt. So they gave me the Ka for NH4Cl. Really, it's the Ka for NH4 plus, that's a typo, is 1.8 times 10 to the negative 5. So we need to find Kb for NH3. So that's going to be equal to Kw divided by Ka. 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. That gives us our Kb. We're going to need this later, so you always have to calculate this. Sorry, this should be Ka. And that'll be Kb. All right, so this is we're finding Ka because this is an acidic salt. Okay, I'm getting a little bit ahead of myself. That's going to give me a Ka value equal to 5.6 times 10 to the negative 10. I hope I didn't confuse anybody with that. I was kind of getting ahead of myself there. Let me write that a little bit better. Ka. And so it's the Ka of NH4 plus. All right, that we're solving for. All right, so just dissociate our salt first. So the salt dissociates into NH4. That's 100% dissociation. Plus Cl minus. So this 100% of it shifts. So if this starts off with 0.10 molar, 0, 0, when the shift occurs, it's minus 0.10, plus 0.10, plus 0.10. So we end up with none, 0.10, and 0.10. Now this is the conjugate acid of that weak base. So we take the cation and we start our equilibrium problem. NH4 plus water is going to form ammonia because it's going to give that and the hydronium ion. Now we'll pick up here in the second part of this lesson.